So this lecture is about our first lecture on magnetostatics. So let me write that down. Magnetostatics. So that's two words. So um, just as non-changing charges, so just as charges sitting around somewhere create an electric field that doesn't change. In the same way, currents that don't vary create a static magnetic field. So non-varying currents create a static means doesn't change with time, magnetic field. So that's the idea behind magnetostatics. Okay. So what does a non-changing current mean? So if I plot, let's say if I measure the current through some wire, so I got a wire with some current going through it, and let's say there's a couple of possibilities there that if I plot that, if I have time here, and I plot the current, if the current doesn't change at all with time, it stays steady, then I have a DC current. Okay, so that causes a static magnetic field. So this is case for static magnetic field, like we're going to be talking about today. And on the other hand, if we have a situation where with time the current is an AC current, so it changes with time, whatever it's doing. So this is AC. So this is I guess you could call it a dynamic or changing magnetic field. So both of these obviously are possible, but we're going to be talking about this case today. So from Maxwell's equation, if you look at Maxwell's equations, the parts of the equations that are describing magnetic field, we have one that says del cross H is the current density plus the change in the electric flux, or you can think of this as the displacement current. So you have the current density, that's the actual current through a conductor, then you have the displacement current that happens through a dielectric or a change in the electric flux. So you have that equation, and then the second equation you have is del cross E is the minus change of the magnetic flux. Okay, so these are both from Maxwell's equations. Now, let's see what happens when you have a static case. So for static case, current is a DC value. So it doesn't change with time. So basically anything that has a change with time goes to zero. In other words, this change with time here, this component, because nothing is changing with time, this goes to zero, and this also shouldn't be changing with time, so that also goes to zero. So those two guys go to zero, and what we're left with is del cross H is equal to just the current density, and del cross E is just equal to zero. Okay, so okay, that's what we have. As an aside, by the way, that if you have that situation, and so if you have del cross E is equal to 0, and we know that del dot D, which is also from Maxwell's equation, is equal to the charge density. So these are all we need to calculate E field. So just this is as an aside, but anyway, we're interested in magnetic field in the conversation today. So basically, if we draw this thing in the integral form, we have that the integral around the closed line loop of h dot dl is equal to the enclosed current. In other words, if you have a current going through the wire and you pick a loop, a closed loop around this wire, and you and then this let's say you have so this a little chunk of this wire would be this DL, and you integrate this all the way around this, and this is a closed loop around this current. So this is H, magnetic flux around that closed loop, over the whole closed loop. That's equal to the current, all the currents that are enclosed. Okay, so that's the integral form of the same equation. And also we have that del dot B is equal to 0. This is always the case because, as we know, there are no magnetic charges. So this is also from Maxwell's equations. And so in a non-magnetic medium, B is equal to mu naught H. Okay, so that's how things look like in a magnetostatic case. So if you have a magnetostatic situation, you have a couple of options to calculate the magnetic field. So first option that we're going to describe, then we're going to do an example, and then we're going to talk about another option, is the Biot-Savart law that we've already described, and that basically gives you an equation for the magnetic flux equal to mu naught I d sub L cross R over 4R squared. Okay, of course this is the full Biot-Savart law is a little bit different. Actually, let me write that down first because that's a more general one. So the general case, it says that the full magnetic field as a function of R is the integral of mu naught the current density, which is a function of R prime. By the way, this is all, we're talking about this in cylindrical coordinates. In this lecture, we're talking about cylindrical coordinates. Just because the reason why cylindrical coordinates tend to be a little bit more popular, I think, with magnetic fields, is that a lot of times you have this kind of case where you have this current, you can sort of model a current as going from minus infinity to plus infinity along a wire, and then you can imagine a cylinder around this. So you can imagine like you have a cylinder of magnetic field around this line. So typically we see cylindrical coordinates used a lot with magnetic fields. Okay, so think in terms of cylindrical coordinates. So we have the current going in the R direction. Then there's a change in sort of it's times the, let me just draw this for you. Let me write it first. and then I will draw it for you. So this is the case where, let's say you have a chunk of metal. Let's see. Let's say you have a chunk of metal like you would have on a printed circuit board, and that's carrying some current. So basically, what you have to do is to integrate that current basically in this sort of cross section going across. That would be sort of the cross section, depending on the current may or may not be uniform along that. You would do the cross of that with R and then 4 over pi r squared, and you figure out the magnetic field around this I don't know, rectangular shape, which is more like a printed circuit board. But in the case where you have a thin wire only, so if you have a simplified case of a thin wire, that makes life simpler, because if I'm going to draw a thin wire in the same way, I no longer have to worry about this current density times this surface. I just basically, my current is I, so that's all I need to worry about. So in this simplifying case where you have just a wire, so in case of a thin wire, then you have a simplified equation for a small increment of the magnetic field is just mu naught I times dl. So again, I've managed to replace this, the current density times sort of the surface or the sort of volume times mu naught. I've replaced that with these current I times dl being the increment on the length of the wire, cross r over 4 pi r squared. Okay, and then if I integrate this, so then b is the integral over a closed loop of mu naught I dl prime cross r over, so I'm going to close dl prime over 4 pi r squared. So again, this is the simplified case. So simplified equation when thin wire carries current. Okay, so again, just also remember that we're in cylindrical coordinates. So basically, again, in the case where you have a DC current, a current that's not changing, the magnetic field, basically, this is kind of all you need to know in terms of a magnetic field. Figuring out the magnetic field, it basically becomes only a function of the current, and what's sort of gotten eliminated is this relationship between electric field and magnetic fields in the case of a DC current. Okay, so that in that case, which again is called the magnetostatic case, this is basically what you need to calculate the magnetic field. Again, notice there's no electric field or electric flux density or something in this equation. So now let's do a couple of examples. So let's do an example. Let's do one example right now. So example of using this for calculation for a few cases. I'm going to do the first one. And you got to be really careful with magnetic fields. They tend to be a lot more, in my my experience, a lot more difficult to deal with than electric fields because of the difficulty for me always is this cross product. So cross product. So in the case of the electric field, you don't have this sort of vector cross products. In this case, you do, which means that the magnetic field is going to be in a direction perpendicular to both this line that we're doing. Sorry, I drew this very wrong here. So this dl isn't here. dl is when you're integrating around a closed loop around this current. So this would be, dl would be here. Okay, so basically you have this cross product would put the magnetic field in a direction perpendicular to both the current and sort of this dl product. So let's take a look at that. Let's take a look at that. So I might be giving it to you in a bad way. So I think it's better if you just look at it in a example. So let's say you have a situation where you have a z. So again, remember we're in a cylindrical coordinates. So let's say you have the z-axis. Remember in the cylindrical coordinates you have the z-axis, and then you have sort of r. So you have r, and you have like phi, and then you have z. So that's cylindrical coordinates. Cylindrical. Okay, so in the case of these cylindrical coordinates, let me write that somewhere else. Let me just replicate it here. Again, let's say I have a case where I have a current that's just running along, there's a thin wire sitting right on the z-axis, and it's carrying a current. Okay, so should I draw this? I guess with black, because the drawing is going to get a little confusing. So let's say the current's flowing along the z-axis from minus infinity to infinity, and I want to figure out the magnetic field in space all around this current that's going across the z direction. Okay, so let's think about, just take any point in space. So let P, I'm going to be a point in space. And then we're going to have a bunch of P's, obviously, right? But let's see what the effect that a magnetic, a current at a section along here would have at a point P, and then we're going to integrate all the different effects and for all possible P's. Okay, so let's say you have this point P, and you are considering the effect of the current from a small increment in the z direction. Let's say that small increment we call dz prime, and it's centered around a point z prime in space, again in z prime on the z-axis. So basically, again, the idea is we figure out a random point, like a random section of the line to a random point P, what is that magnetic field? Then we're gonna look at the effects of all, we're gonna integrate over the whole line and then look at all possible points, P. Okay, so because this is cylindrical coordinates, we're kind of, the way what we're doing is we're imagining this point P is on a cylinder, okay, that this is not an actual cylinder, it's an imaginary cylinder, right? So you're looking at how this point P is, because it's the magnetic field we know is going to be, if you have current flowing here, we know the magnetic field is going to be sort of cylindrically symmetric around this. So you can kind of think about all points on a particular cylinder are all these points are going to have the same magnetic field. Okay, this whole surface of the cylinder around it, or all those points are, they look exactly the same. They have the same amount of current above them as below them, because the current goes from minus infinity to plus infinity. And if there's another point P here on the same cylinder, same distance, it's gonna basically feel the same. You're basically gonna have the same magnetic field there than you would have at any point. And then you can think of this as a series of concentric cylinders, and on any of those cylinders, the magnetic field will be the same because of symmetry. Okay, so anyway, in this case, so we assume we have a cylinder. So P is on any point in space, and you can think of P is on a cylinder, and all points on that cylinder will have same H and B, because the cylinder is symmetric, is totally symmetric around the wire I, which is on the z-axis. Okay, so I mean, it's no coincidence because we defined that cylinder, so it's fully symmetric. Okay, so in that case, what we're trying to do is, again, figure out the effect. So look at this, going back to this Bayes-Savatt law. Oops. Going back to this increment. So we're trying to figure out the magnetic field on this point P caused by the small increment of, I keep drawing the Z in a bad spot, so never mind me. This is this DL. Again, I had it written out correctly before. Sorry, guys. Sorry to change this twice on you, but that's actually this unit DL coming from the current. So we're trying to figure out the effect of this small chunk. If we call this DL, if we call this DZ prime in this case, we're trying to find the effects of this current on this point P, and then we're going to integrate along from minus Z to plus Z. So, okay, so first, as usual with these things, we got to figure out the vectors. And so if you look at where this point P is you end up with, so if you're looking at the sort of the field vector, you have to draw it from here to this point P. Let's call that R. But what we really want is this vector Okay, so we need to find what that vector is. And to find it, so what we do is, so this vector ends up being, so we need to find, let's see what to draw that. Orange already have. Let's use red. So I want to find this vector r. So I want to find this vector r. Okay. So that r is this vector r minus this vector. Okay, so this vector is this vector minus this vector. Okay, so this vector, I'm going to call this guy r prime. So I'm going to call this vector r prime. So to the vector sign, so r prime is z prime, so it's this distance times the unit vector in the direction of z, and r, this guy, because we're in the cylindrical coordinates, r hat is equal to a in the direction of r, which is basically this guy in the direction of r, plus z hat. So this is the location of P with respect to the origin. This is the location of the current increment that we're looking at right now. Okay, so, and then basically if you want to figure out this vector r, okay, in the Biot-Savart law, and the r squared is basically the distance from the increment of current to the point. So that point would be this vector from this increment of current to this point. We could also be looking at this increment of current to that point, or this increment to that point. So we haven't really defined it, but for every point along this z axis, we're going to have a different z prime and dz prime, and then we're going to integrate over the whole thing. So r hat, or the r vector is r minus r prime. So it's equal to, if I plug these, basically using those, I'm going to have z prime z hat minus, we're going to have a r hat plus z hat minus z prime z hat. So this is equal to a r hat plus z minus z prime z hat. So that's r from that chunk of current. Okay, so if I use now this guy, so I'm gonna copy this dude over. So let me plug in the values. So dB is mu naught I over 4 pi. So, and then it's dz prime z hat. So that's this dl. and cross of that with R, which is, sorry, I shouldn't have written R hat. This is R. The R hat or R? Let me see. Maybe it is R. It's basically R, so I wrote this stuff wrong here. So it's R vector, R vector, R vector. Okay, cross a R hat plus Z minus Z prime Z hat over, so this is, now I gotta write R squared, so let me first write it down and then tell you guys how I got it. So it's over A squared plus Z minus Z prime squared. No, sorry guys, sorry, this guy is R hat, these are R hats. Keep going back and forth with this. So this is R hat, R hat. Okay, Z minus Z prime squared to the 3/2. Okay, so how did I come up with this? Well, I wanna basically come up with this guy. So sorry, R hat over R squared. So I want to figure out R hat over R squared. So R hat is the vector R over the amplitude of the vector R. That's the definition of capital R hat. And 1 over R squared is the amplitude of the vector R squared. So if I want to have R hat over R squared, which is this guy, that will look like 1 over R hat squared, R hat over amplitude of R hat. So I'm just plugging this guy in for this, and this guy in for that. And I'm gonna end up with R hat over R hat cubed. And R hat amplitude is A squared plus Z minus Z prime squared square root of. That's coming from here. So if I want to figure out the amplitude, it's coming from here. If I want to do the amplitude, it's just these two square root of, square root of. And so R hat cubed is A squared plus Z minus Z prime squared to the 3/2. So that's how I end up here. Okay, now also need to put in a direction for B. So again, notice we're this vector dB, we've got this cross product. Well, I guess the cross product will tell us where that is, but so thinking of this, okay, where will be the direction of dB? So if you look at it, I have two cross products here. One is Z cross with R, and one is Z cross with Z. Well, Z crossed with Z, Z hat crossed with Z hat, that's easy because that's just equal to 0. So if two things are, basically cross product is giving you an idea of how close two things are at 90 degrees from each other. And if they're parallel or they're the same thing, then it's basically the cross product is 0. And since we're in the cylindrical coordinates, basically when you have basically in cylindrical coordinates, you have z hat, you have r hat, and you have phi hat. So if you have cross product of z hat with r hat, that's going to give you something that's in the direction of phi hat. So we're gonna be in the direction of phi. That's where this dB is gonna be. So to write the dB, so back to dB here with all this good stuff in there, is equal to phi hat mu naught I dz prime over 4 pi a squared plus z minus z prime squared, the whole thing to the 3/2. Yeah. Okay. And then to get the full b, we need to integrate from z prime going from minus infinity to plus infinity. So dv. So basically b is gonna be the integral of dB from z is equal to z prime being from minus infinity to plus infinity. So that's equal to minus infinity to plus infinity v hat mu naught I dz prime over 4 pi a squared plus z minus z prime squared to d 3/2. So that basically gives us the magnetic field. So I'm not gonna do the integral, just gonna give you the answer for the integral. So answer is B. So this is the magnetic flux at any point P is in the phi direction. So basically it's in the cylinder, or sort of you get this right hand rule. If the current is going in the direction of your thumb, you get the magnetic field in the direction of the rest of your fingers using the right hand sort of twist rule, and that ends up being mu naught I over 2 pi A. And this, if you remember, A is basically this radius of the cylinder. So A is any radius basically. So it's any distance away from. So A is radius for any cylinder. So if I was gonna replace it with R, so the magnetic flux at any point in space is phi bar mu naught I over 2 pi R along the line. So if I was gonna draw this thing, it's easiest to draw it so from the top. So let's say this is the current coming out of the screen in this line. So imagine a line that's coming out of my screen, going to plus infinity, and going into the screen from minus infinity. So it's basically this same line, except I'm looking at it from the top down. So if I look at it from the top down, I'm gonna see a bunch of magnetic field lines that are going, That's not much of a cylinder looking thing. That's sort of cylindrically symmetric around, going in the direction of phi around that filament, and as I move away from that current, the magnetic field gets smaller and smaller as you go across that anyway. So basically you have, what this equation tells you is the magnetic flux around a wire that's carrying a current I is, so again, this is coming out of the screen, this is the line, and so the direction of the magnetic flux is going around that wire, and as you get further and further away from the wire, the value or the strength of that magnetic flux is going to go down. So that's ends up being the answer and what it would look like. So given that this is a real symmetric situation, we could have also used Ampere's law, which would have made a much easier answer. So if you think about if you consider the symmetry of the problem, situation, you could have also used Ampere's law. And so just what does Ampere's law look like? And the reason you can do that is because you can see that if you have this case where the current's coming out, basically you have a single wire coming out of the screen going into the screen, that the magnetic field is going to be in this phi direction, and only is going to be its strength is only going to be a function of r. So if you see the symmetry of this situation, you realize is h is in the phi direction and is only a function of r. So h is only in direction of phi. Again, remember, we're in cylindrical coordinates, and is only a function of r. So basically, then you can basically use Ampere's law, which is this guy. You can use this integral form of Ampere's law. And so you would end up with, so again, you have a wire here with a current, and then you know that the magnetic flux is basically going around that thing, and it's function of r. So basically, so let's say if this is C, a closed loop, you integrate the magnetic flux times r d phi is equal to the enclosed current, which is I. So h phi is equal to I over 2 pi r phi hat. And B is equal to mu naught I over 2 pi r phi hat. So which is just exactly the same as what we got with Biot-Savart law, but in this case, what we did is we used the symmetry of the sort of a symmetry argument instead of doing the vector cross product, which was like the full mathematical way of doing it. I guess this is a mathematical way too, but you just have to talk yourself into knowing ahead of time that the magnetic flux is in the direction of phi and is only a function of r.